Question number 32. Use the graph of the first derivative that you see to graph the second derivative and the function. So when I look at the first derivative, if I want to graph the second derivative, it's all about slope. So the first part here is a line, and the slope is 2. No, up 1 over 2. The slope is 1/2. So, as I come over here, I'm also looking at increasing and decreasing and a turning point, or where it's undefined. So, if I want to graph the second derivative, this is going to go to what number? 6. So the first thing I look at, it's a line. So from here to here, the line has a slope of 1/2. Then I notice, in fact, there's going to be a hole here, because what I notice is that the derivative doesn't exist at 2 because of the cusp or corner. And then what do I notice? It decreases all the way through from there. And if I think of where it's steepest, where is it steepest? It's steepest, and then it kind of flattens out. So this part has the most negative, and this part has the least negative because it's steeper here, and then it curves in terms of what's happening here. You can even do this. But that idea. And it's undefined there. You could also put a hole here and do that same action. And there's the graph of the second derivative. To graph the derivative, again, I'm counting to 6, right? 1, 2, 3, 4, 5, 6. This takes practice and not giving up, all of that. When I look, I need 2 number lines. So for the first derivative number line, it goes from 0 to 6, so no endpoint. We need endpoints. We have an x-intercept at 3, and that's it. And then it's above and below. So that means that 3 is a maximum. And then when I look at the second derivative, at 2, there's a turning point, and then it increases and decreases. So there's a point of inflection at 2. So it increases up to 3. So I don't have a starting point, but I know it increases up to 3. So there's my 3. And I know it increases up to there, and then it decreases back to here. And now it's just a matter of connecting with the right curves. So it's concave up, and then it's concave down. And there it is. Number 33. Sorry, this was 32. It says find the cubic function. So it's y equals ax cubed plus bx squared plus cx plus d. It has a max point at 0, 2, and a point of inflection at -1, -2. All right, so let's plug in this point, 0, 2. If I plug in 0 for x, that means d is equal to 2. So I've already figured that out. Plug in 0 for x, only d is left, and it's equal to 2. So y equals ax cubed plus bx squared plus cx, and then we have the 2. Next, I'm going to plug in -1 and -2. And then I'm going to simplify that. So I know I'm going to subtract 2. This is -a plus b. -1 squared is positive, and minus c. We'll hold on to that for a second. Now I'm going to take the derivative. if this is a max point, when I take the derivative at 0, the answer is 0. So if I plug in 0 for x, the answer is 0. So the derivative is 0 at a max point. So that means c is equal to 0. So because of that, I now have negative 4, negative a plus b. So again, I plug in 0, and I make it equal to 0, and recognize what the answer is. So if I plug in 0 and make the derivative equal to 0, that's what c equals. So we know what c equals. We know what d equals. So now I have 2 left. So I plugged in 0 for c here. I'm going to take the derivative again. So 6ax plus 2b. We have a point of inflection when x equals negative 1. So I make it equal to 0 and plug in negative 1. So now I have negative 6a, negative 2. So now I need to solve this. I'll multiply by, well, I can solve for a now, right? So what am I even doing here? So if I solve for a here, I can add 2 and divide by negative 6. So a is equal to negative 1/3. No. What did I do wrong? I know what I did wrong. So what I did wrong is I didn't have an x here. So I had no number to plug in for x. So I just have a b. So ignore this part. It's negative 6a plus 2b. And now this is what I solve. I'm going to multiply the top times 6. Or negative 2. Let's do negative 2. So multiply the top by negative 2. Add them together. I get a equaling negative 2. So I divide it by negative 4. What's left? B. So I'm going to come back into any one of these. So I'll go right here. So if a is negative 2, a negative times a negative is positive 2. Subtract 2, and you have what b equals. B equals negative 6. So if I summarized it, a is negative 2, b is negative 6, c is 0, and d is 2. There you go. Quite a question. More algebra than calculus. All right, 34. Now for that. In 34, a box is to be made by cutting small squares from each corner. The box is 3 feet by 5 feet. I'm just going to label it right on here. You should draw it in your notebook, this diagram, and label it 3 and 5. Find the size of the squares that will produce a maximum volume. So this is going to be the width. And that width right there is 3 minus 2x. This right here is going to be the length of the box. That's 5 minus 2x. And then this part right here is just x, and that's going to be the height when you fold it up. So these are the dimensions for the volume. We're going to use our calculator. So the volume is length times width times height. Our goal is to take the derivative equal to 0 and solve it to get a maximum value and make sure that the answer I get is in my domain. If I plug in x, I can't have a negative dimension, so I got to be careful about that. So I'm going to solve an equation. So I'm going to go menu algebra solve. I'm going to do the derivative. So I press the button beside the 9 just to directly get the derivative. Highlight over that. And I want, this is going to be, I could change the, it's x. So what is it? 5 minus 2x. 3 minus 2x. I'm going to put parentheses around the x too. Makes it easier so the calculator knows you're multiplying. We're going to make it equal to 0, comma x. Control enter. So there are two answers there. 2.05 is too big. So if I plug 2.05 in here, 2 times 2 is negative 4. So that would produce a negative length. So this is not in my domain. This is the only correct answer. So the correct answer is when x equals 0.607. If I want to know that that is this is actually the other end. If I plug in 3 over 2, you get 0. So it has to be between 0 and 3 over 2. That's 0.607. I think this is a good skill to have. So I'm going to show you that if I want to know if that's a max or minimum into this, you can use the second derivative to tell. So instead of doing, I did a number line there, but really, if you did the second derivative at 0.607, if that's less than 0, then that's concave down and creates a maximum. So if I did the same work here, so if I went menu, this time calculus, derivative at a point, and the value I'm looking for is 0.607, and it's really the second derivative that I'm looking for. And then I type it in again. So 5 subtract 2x, 3 subtract 2x, and x. And then recognize that when you do the second derivative, the derivative's negatives. It's concave down there. So that's another way to show that this is a maximum value. And that might be quicker than doing a number line. But it's good to have that skill. 34. I did 34. This was 34. 35. Find the volume of the box. So we just found the x value. So just plug in 0.607. Use your calculator. I'm just going to use my answer key. So just plug it in, and the answer is about 4. It's 4.104 feet cubed. So it's about 4. It might, the decimal might be off a bit because I used a rounded answer in there, but it's about 4. 36. Turn the page. We're almost there. In number 36, y equals x over x plus 5. The equation of the tangent line, find the equation of a tangent line. So x is negative 6. The y value, so if I plug in negative 6 for x, that answer is positive 6. And then the slope is found by doing the derivatives. Now the derivative here is going to be the quotient rule. That's the bottom times the derivative of the top minus the top times the derivative of the bottom and the bottom squared. X times 1 and negative x, they cross out. 5 times 1, that's all you're left with. So if I distribute and combine like terms, x and negative x cross out, 5 times 1 is what remains. Only need the x value that you plug in here. Recognize it's going to become positive 1. So the tangent line is 5x plus 6 plus 6. And the question is, use that to estimate negative 6 1/5. So if I plug in negative 6 and 1/5, negative 6 and negative 6, you're left with negative 1/5. You need to have a little bit of number sense there. The 5s divide out, so it's negative 1 plus 6, so the estimate answer is 5. 37. Without using a calculator, darn it, graph this thing. So you have a function, you have the first derivative, and a second derivative. So we're going to use all of it. So we're going to do pre-calculus and some calculus and see what do we get from each one. And the more we practice, the better you get. And you see it's kind of like a jigsaw puzzle that you're putting together and that you have more skill to be able to put it together. So for the function, the things I'm looking for is what's the domain. And I can see from the denominator x can't equal 0. Another thing I look at, there's nothing removable. So that means there's a vertical asymptote at x equals 0. That's the domain restriction. When I look at the numerator, x cubed plus 2 equals 0, I'm going to solve that. And so when I solve it, I get the cube root of negative 2. That's a little bit less than negative 1. So this is like negative 1.2 or something. The cube root of negative 1 is negative 1. So the cube root of negative 2 is like a little more negative than negative 1 to estimate it. So it's somewhere between negative 1 and 2. There's my estimate. The y-intercept, none, because when you plug in 0, end behavior. So when I look at the end behavior, x cubed divided by x, the end behavior is going to act exactly like x squared. So both ends are going to go up. All right, so that's the pre-calculus part. The derivative, this is increasing and decreasing. So what are my critical numbers? So when I look at the numerator, I need to make it equal to 0. When I solve this, that's a 3, right? Add 2 and divide by 2. And then when I cube root it, I get the answer 1. So when I do a number line, 0 is undefined, and 1 is a critical number that could be a turning point. This, to remind yourself, is an asymptote. Then, into the derivative, I'm going to plug in a negative number. So that's a negative divided by a positive. I'm going to plug in a half. That's a negative divided by a positive. And then I'm going to plug in like 2 or 3 or 5. And that's a positive divided by a positive. So at 1 is a minimum. So we're going to find that. To find the y coordinate, you plug 1 in for x, and you get 3 over 1. So the minimum is at 1, 3. Now the second derivative, we get concavity here. Take the numerator, equal to 0. Now what you're going to find is, when you cube root it, it's the cube root of negative 2. It's the x-intercept that is that. Right? We found that, the x-intercept. So it's about negative 1.2. That's our only critical number. And we need 0 here too, where it's undefined. Oops, negative 1.2 is on this side. And then if I plug in like negative 5, you got to plug into here. So plug in like negative 10. And it's a negative divided by negative, so it's concave up. Plug in negative 1, and it's a positive divided by negative. And you plug in a positive number, it's positive. So there's the concavity. So there's a point of inflection there in terms of concavity. Now we're going to put it all together. I like it for you to press pause and try to put all the pieces together, and you try first and then press play. All right. So we have x-intercept and point of inflection somewhere around there, negative 1.2. We have a maximum at 1, 3. and we have an asymptote at 0. The end behavior, both ends are going up. So we have a minimum here. We know it's concave up and then concave down. And it's decreasing all the way through. So it's concave up and then concave down, and it's decreasing all the way through. On this side, it's concave, it's decreasing, but the concavity is all concave up. And there's your picture. So you have the concavity, it's decreasing. You have the concavity, it's decreasing and then increasing, and we have a minimum, or a minimum at 1, 3. What do you think? All right, 38. That's a good question. Without using a calculator, darn it, find the intercepts, extrema, and points of inflection and draw the graph. So, actually, I don't mind not using my calculator. To do that, I'm first going to start with this. Take the bars away, and we're going to analyze this. So, start with the pre-calculus part. So, the pre-calculus part, there's no domain restriction, so it's continuous. That's a good start. The end behavior is the power term, which is y equals negative x cubed. So it goes down to the right and up to the left. We're going to change that when we reflect it. The x-intercepts, I make it equal to 0. And I solve it. So I'm going to solve by factoring. So I'm going to factor out a negative x squared. And know that my intercepts are at 0 and 3. This one is even, and this one is odd. So it touches and then it crosses. The y-intercept is at 0, so when you plug in 0, you get the answer 0. So that's all for the pre-calculus part. We're now going to take the derivative, negative 3x squared and 6x. Make it equal to 0 to find the critical numbers. We're going to factor out negative 3x. Oops, that's a minus 2 now. And so the two answers are 0 and 2. So into this, notice the odd multiplicity. So a negative answer, a negative times a negative is positive times a negative. So make sure you get the first one right, and then the signs change. So there's a minimum at 0 and a maximum at 2. Now I got to find the y-coordinate. So if I plug in 0, the answer is 0. For the maximum, a little bit more work. Plug in 2 at 12 and negative 8. So that's 4. So that's not bad. So 2 and 4. Last thing, the second derivative. That's negative 6x plus 6 equals 0. So if I solve it, the answer is 1. That's the only critical number. So for the second derivative, if I plug in a negative number, or if I plug in like 5 or 6 or whatever, there's a point of inflection at 1. And if I plug in 1, I get the answer 2. All right, we're going to put this together. So these are the things I look at. So anyways, I'd like you to again. Can you, I'd like you as well to graph this before I do it. So press pause and graph it. And then let's see if we did it right. Or if you need to start the graph, well, try it first and then press play. And if you need some support along the way, I will. All right, so I'm going to start with the intercepts. All right, so first of all, it counts to 3. So 1, 2, 3. This goes up to 4. Okay. So we have an intercept at 0 and at 3. This graph, and we also have a maximum at 2, 4. and a point of inflection at 1, 2. So those are the points I have down. This decreases and it's concave up all the way to 1. So there it is. It decreases, creates a turning point, and all the way to 1 it's concave up. After that, it keeps increasing to 2. And after 1 it's concave down and creates a turning point. Now, normally it would continue down this way, but the absolute value reflects that up. And there it is. So anything that was below gets reflected up. This now, just by doing that, I've now graphed this. So that's what the graph looks like. Last one. I bet you never thought you'd get here. 39. There is no other way in mathematics, science, and these kind of things, reading too, whatever, you have to practice, right? And you have to consistently practice what you do. I know a lot of you are in sports, and when you practice and have your practice time, and it's 2-3 hours a day plus, think of what it would take to be good at mathematics. Think of it like a sports team, right? How many hours you spend at it and care about it and practice it. That's the same thing. All right. 1, -2 is a point on the graph y squared minus x squared plus 2x equals 5. And it says find the derivative and the second derivative. So I need to do this implicitly. So it's 2y, it needs a y prime. -2x does not, 2 does not, and 0. To get y prime by itself, I'm going to add 2x and subtract 2. And I'm going to divide everything by 2y. Because I'm going to do work with this, I'm going to divide everything by 2 just to make it easier to work with. So I get x minus 1 over y. Then it says use the point. So I'm going to use the point 1, -2. And the first derivative at 1, -2, plug in 1 and -2, and you can see the answer is 0. That means this is a critical number. So it could create a turning point because the derivative there is equal to 0. Now do the second derivative. So for the second derivative, it's the bottom, it's the quotient rule. The bottom times the derivative of the top minus the top. Oh, let me do it from the other one. Sorry. I was doing it from this one. This one. Let's try it again. So the bottom times the derivative of the top minus the top times the derivative of the bottom, but it needs a hook, and then squared. Now, we know that when we take the second derivative at -2, that when I plug in 1, -2 for the first derivative, this answer is 0. In fact, when I plug in 1, the answer is 0. So this is y times 1. I'm going to plug in -2 for y. When I plug in positive 1, 1 take away 1 is 0. And 0 times, this is actually 0 too, that's just 0. So I have nothing at the end there to subtract. And then the denominator is -2 squared from the y coordinate. What matters here is that this answer, the second derivative at 1, -2, is less than 0. And because it's less than 0, and because it's a critical number, this is concave down. So at 1, -2 is a relative maximum. And that's using a second derivative test and using concavity to know that, first of all, it's a critical number because it gives you the first derivative is equal to 0. Then when I do the second derivative, it's a negative when you plug in 1, -2, which means it's concave down, which means it's a maximum. All right, we did it. Mr. G Math over and out. I'm proud of you for finishing this long assignment and working on calculus and being better. Till next time.